after spending a bit of time reviewing in a somewhat more recent and modern way classical Tikhonov regularization, in the last few classes we encountered a different way of regularizing. We discussed essentially regularization by optimization or by iteration. And we discussed a bunch of different views on this. For example, considering a spectral filtering perspective. This kept us busy until last class. We start taking it a step further, which is going beyond what one may call batch gradient method. Basically, method that weight all the data until they actually provide a potential candidate answer into what might call online methods. Okay, these are methods that learn one point at a time. So they do provide an estimate of a possible solution every time they get a pair X and Y. The small comment we made the other time is that clearly you can make anything. If you are inefficient enough, you can make anything online. You just start from scratch anytime you get a new point and recompute everything from scratch. So inherently, when we talk about online learning methods, or let's say most of the time when we talk about online learning method, we not only have the idea way learning one point at a time, but somewhat don't learn from scratch. So iterate the learning process by basically updating what we've been doing so far to get a new solution. And the reason for this is essentially computation. We like not to throw away computation and repeat computation all the time, but just hopefully do a small amount of computation to get a new solution once a new point arrives. Okay? The comment I made the other time, and today we're going to see it even more closely, is that there are at least two orders of reason to do this. One is because you may have actually data that arrive streaming. Okay, so the classical example these days is online advertisement. You click, you click, you click, you click, and they want you to click something else. So there has to be an instantaneous response of what's going on. The other situation you might be interested in to looking at the data one at a time is when your data set is very large and is lying on your disk, but it's cumbersome to just load it all in memory at once. So of course you can take chunks, but in the stream case you might want to take one point at the time so that you can make the memory usage more efficient. Shouting. You should. So the algorithm we start introducing that does just like that, just this, it updates the solution, is what is called recursive least squares, and is perhaps one of the most classical examples. These two lines describe what is this method doing. Is essentially the key difference with respect to standard gradient methods is here. Okay, if you consider this forget about the gamma. If you consider this quantity, this is essentially the gradient of the loss function at the point. Okay, if I write down least squares. And I now take the gradient with respect to W, I get something that looks just like this. And this is in contrast of what happens if you actually consider the empirical error, where if you take the gradient, you don't get just one element, you will take the sum of all of them. Okay? So if you do standard batch gradient, what you do is that you actually compute many of this quantity, exactly n of them, before you update your solution. Whereas here, after you see just one, boom, you output the solution. Is it clear? In this formulation, this kind of step size is a big step size in the sense that it's not just a constant, it's a more complicated step size. It's given by a matrix, which is itself given by a recursion that I write here. Okay, so this is not just a simple incremental stochastic gradient that we're going to discuss in a minute, but it's called recursive least squares because essentially it actually has a more complicated form, which is derived exactly from the ordinary least squares. So what we are computing here is not an approximation, but is exactly. So if we denote with X the data matrix, so this is the n by p or d data matrix, this is the n by 1 vector of outputs. This is an identity. Okay, these two quantities are exactly the same. I'm not approximating anything. I'm just computing. And there are just two different ways of computing things. Okay, so option one is I compute this for n. You get me n plus 1. I build the whole matrix and I recompute the whole thing. Or I run this and I just update what I've done before. Okay, and this is exactly the way we derive this. Do you remember what was the beginning of the derivation of these two iterations, we started exactly from this. And what did we do? Anybody remember? Starting a lot. Anybody remember? So the basic idea was to write this, then write wn minus 1, which is exactly the same form. It just, instead of n points, you have n minus 1. You subtract these two quantities, and then you do some basic linear algebra. Okay? That's what we did last time. Let's see if I wrote it, because I think I did. I mean, it's easy to remember, because basically what you get is exactly this. Okay? So if you do wn, if you use this expression and you write the one for wn minus 1, and you do wn minus wn minus 1, you get exactly this quantity. Sorry, yes. Again, it's useful to remember that this quantity is just what you might call the covariance matrix. So x transpose x is what you might want to call sigma n, and is just given by the sum of xi transpose. Whereas x transpose y is just the sum of xi yi. Okay, these are vectors and these are just numbers. So you just write it down, wn, you write it down wn minus 1, you subtract, you massage a little bit, and then you get exactly that expression. Okay? What we were left doing is getting this expression. Because you see, otherwise every time I would have to compute this. So basically what we find out is that in this expression, gamma n is given by the matrix to the minus 1, the covariance matrix to the minus 1. Okay? So if we didn't have this one iteration, this would be a little useless, because it means that every time you get a new point, you have to recompute this inverse from scratch. Okay? So I solve the problem for n minus 1 point, then I get a new point. First I have to solve anyway a new matrix, and then I do the update. Those will be pointless. Okay? So the key point is actually to try to find a way to suppose that you actually obtained already this. Okay? Can you do? Can you now update this computation to get to the gamma to n to the minus 1, which is your gamma n? Okay? And this is a standard question in linear algebra. It's basically what is called the rank 1 update. And so we're just going to recall it's a standard thing, but it's, in case you have never seen it, it's useful to see it once. The basic idea is that there is the following recursion formula. So here A, B, C, D are generic matrices for now. And what we have is that if you have a matrix which can be written this way, as A plus B, C, D, what you have in mind is that this is, well, we'll see what you have in mind. Let me first write the equation down. Then you get that this is equal to A to the minus 1 minus A to the minus 1 B. Then you have D A to the minus 1 B plus C to the minus 1 D A to the minus 1. Okay? How should you think about it? If you already have the inverse of A, I'm going to tell you how to actually get the inverse of A plus BCD. And this is what's going on here. Okay? You already have the computation for A to the minus 1. Let me try to invert this whole thing now. In the particular case of interest where these BCD are actually a vector outer product of another vector. That's what so it's a matrix, but it's rank 1. And that's exactly our case. So let's recognize that oh, let's keep it written in here, that sigma n has exactly that form. Can we write it in that form? So I would like to know how to write sigma n, the covariance matrix, in such a way that is written as some A plus some BCD. Okay. Well, okay, so clearly I would like to be able to put here n to the minus 1. What am I left to put in? Okay, so sigma n is this with 1 to n. N to the minus 1 is just to 1 to n to the minus 1. Okay, so I still have the last term of the sum to add to that equation. So it is plus xn transpose. So what is B, C, and D? It's particularly easy. B is just xn. Okay, A is just sigma n to the minus 1, sigma n minus 1. B is simply xn. C is the number 1, because these matrices are vectors. And D is just xn transpose. Okay, that's it. So now you just go down and you write down what you get if you plug in this identification. Okay, so A, B, C equal 1, and D is equal this. Okay? So back there, do you see up to here? So here you clearly don't see, because I see you doing like, but say here is okay, up above here is okay. So roughly this is the no return line, correct? Is that okay? Above here is fine? Okay. Now you might wonder, what is written here? So let me write it here. So sigma n equal sigma n minus 1 plus xn transpose. Notice the improvement in the quality of writing also. So I want to call this A. I want to call this B. I want to call this D. And I want to call the invisible number 1 C. Okay? And I'm going to write it, but while I write it, you can just notice that I'm going to write what is written here. Okay? So I'm just going to rewrite it because I want to do but that's it. Because basically I have A minus 1, okay? Yes. Here. Yes. You're right. Thanks. Yeah. Minus 1 forgot. Okay? You got this, then you get sigma n to the minus 1, then you get xn. Now, what is this stuff in here? So plus 1 is a number. So c minus 1 is just 1. It's a 1 inverse, okay? And then this stuff has to be a number 2. What number is it? Is d, which is xn transpose, times a to the minus 1, which is sigma n to the minus 1, times b. So it is exactly what it's written. So it's like xn. It would be transpose. We use this other notation instead. Plus 1. So this is the term in the parentheses, which rightly so goes in the numerator. Okay? And then I still have to write this, which is just xn transpose sigma n to the minus 1. Okay? I just have to identify the object, and that's it, and it's finished. Then at this point, this is the way we derive it, so it makes sense to write it like this, but I can just say, okay, I'm going to start iteratively from the beginning. I'm going to start with the identity, and I just update, and so I rename sigma n to the minus 1, gamma n to the minus 1. Okay, that's all. Okay? All right? This, we look at this because it's classical, it's simple, it's an excuse to look at least two matrix identity that you might want to use all the time, which is this kind of common denominator for matrices, and Sherman-Woodbury are very useful ones. Okay, so there's something. What we want to do today is to finish this discussion introducing stochastic gradient, and then move on to large scale, discuss a little bit what you do when you have large scale problems and you want to try to use kernel methods. Okay. So before we do that, let's just comment on this and just say what we like and what we don't like of this method. And I meant you say what you like and what you like on this method. It's online. Yes, it updates. You don't just restart from scratch every time. So we kind of like that. I guess it's simple enough. You know, it's just a simple thing. There's no approximation. I'm actually computing exactly the 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 ordinary least squares. Okay, I'm doing this. There is no approximation. It's just another way to distribute computation. It's much better. You know, I check what happens if you have to invert the matrix every time you get a new point. It's insane. So I guess this is the stuff I like. Yes. Right, so that's the thing that we don't like, and that's the way you fix it. Okay, so one thing that you might say is like, look, to do everything here, I am writing inverse all over the place. Okay, so what's going on here? I mean, what if it's, you know, what if things are not invertible? What do I do? Okay, and the basic idea is that we did this for the sake of simplicity, because you see, this is true just like this. But you know, one way you can do is to say, no, sorry, I was kidding. I'm actually not shooting for this. I'm shooting for the regularized version. Okay, so rather than Wn equal xn transpose xn minus 1 xn transpose y hat, I'm actually shooting for this. Okay? You know, we are just looking at this as a solver, which is online, and this is a solver for regularized least squares. So one thing that you don't like, and you should complain, is that I made an assumption that things were invertible, and the comment that the question basically points to the answer to this complaint. Okay, basically saying, well, we are not going to do that. We actually do this on the regularized, and it's an exercise that you almost can do visually. Convince yourself that nothing changes. Okay, you're going to have it basically just that everywhere you see sigma, you're going to have sigma plus lambda. That's all. Okay, so there are going to be some micro adjustment to this discussion. The rest is, and you know, you could just do it as an exercise to learn this calculation. Okay. All right. So this is one thing that we don't like, and we fixed it. Okay. What else? I guess one comment in practice is that nobody actually really does this in practice. It's known that these kind of updates have some kind of unstable, a little bit unstable from a numerical point of view. So typically what people do is, and I'm just going to say this as keywords to look up if you're interested in actually using this, is basically considering what is called the Cholesky decomposition of this matrix, and then do this kind of rank 1 update on the Cholesky decomposition. Okay, this again is a standard bit of numerical analysis that we don't want to discuss here because it's a bit beyond the scope, but just as a warning, you typically don't really do that. You do something like that on a decomposition of the matrix you want to invert, okay, or the problem you want to solve. Another comment you want to make is we're not going to do it because again it's an exercise, but you can kernelize all this. Okay, we taught at this point a bunch of times how when you have an iteration, you can actually use induction argument to show that you can kernelize. You can use the same argument here. Okay, today to save time, we're not going to do through it, but it's exactly the same argument you used to when we did say logistic regression of SVM or early stopping for square loss for you know, early stopping for gradient descent with the square loss. It's exactly the same stuff. Okay. I think this is basically these are the main comment for this. I guess the other big, yes, go complain. Well, let's say, you know, it's a bit late for this question because we've been doing this for almost a month now, but ignoring this fact, suppose that this matrix is diagonal just for the sake of simplicity, okay? So it's not going to be, but we're going to diagonalize it. So assume for now that it's diagonal, okay? It's diagonal. It means that it's a big matrix with numbers, sigma 1, sigma, I guess, p, and nothing else, okay? What do I mean and I order them. The first one is the big one, the last one is the small one. What does it mean to invert this matrix? It means that I take this number and I put 1 over. Okay. What does it mean that it's not invertible? Is that I get a 0 here, and when I go 1 over, it goes to infinity. Okay. And if I now, instead of just inverting this, I add a plus lambda, what does it mean? Well, nothing. It means that when I do 1 over, I have again, let's do it in 2 steps. It means that whenever you see sigma, you actually have sigma plus lambda. I'm just adding 2 diagonal matrices. And now when I want to invert, I'm just going to do this. So if this guy is small, it doesn't matter. Okay? Okay, and you can say, okay, but this does the diagonal case. Sure, but if you now consider whenever you have a matrix, which is you can diagonalize to understand what's going on, you can actually consider the eigendecomposition of the matrix. Okay, so if X transpose X has this decomposition, when you take an inverse, it means that you're doing the operation on the inner. There are too many sigmas in this story. Let me. Yes. Okay, it means that you're doing the same thing here. So, and again, if you add you have some diagonal, you have to always think about this. So the nice thing about diagonalizing matrices is that you can basically think as if everything was diagonal and everything was real numbers in the end of the day. It's just this operation. Okay, so this is it. Yes. No. So I'm not. I don't use collection decomposition instead of a rank 1 update. I use a rank 1 update of the collection decomposition. So here I'm basically telling you, in this reasoning, I do an inverse and then I do a rank 1 update on the inverse. Instead of what I'm saying is, no. Do a collection update, do the rank 1, do the collection decomposition, do the rank 1 update of that, and then invert and keep on going. Okay. So it's not, the rank 1 doesn't replace Koleski or the other way around. It's like inverse plus rank 1 or Koleski plus L1. Okay? Well, 1, I'm not sure what I'm saying. Rank 1. Okay? All right, so the one thing that we really don't like in all this story, okay, is that if efficiency is our concern, we have to carry around something big, which is this matrix gamma n. Notice, think a second about how this learning process will proceed. I get the point, and what do I have to keep? I get x1, y1, and then what do I do, and what do I have to keep in memory? No. Yes. Yes.
You need WM.
Right, the truth is that probably I don't need to keep them both. Yeah, but anyway, so the main point is that I need W. I need the current pairs of points. These are vectors of length P, so it's hard to imagine you can do much less than that. But then you need this guy here, okay? So it's kind of nice because it means that every time you get the point, you perform a computation, you say something, and you can throw away that point, okay? You can just throw it away. But you still have to carry this stuff around, and this is as big as the number of features you have. Okay, if you kernelize, you might hope to reduce the size of that, but still you have to carry a matrix around. Okay, essentially, when one goes in the direction of stochastic gradient methods or incremental gradient methods, it goes in the direction of solving exactly these kind of issues at the price of performing an approximation. So what you do is that one start to consider instead things that looks like this. T equal Wt minus 1 minus gamma T xit Wt minus 1 minus yt. Okay, so we want to make 2 comments about this that I just wrote. Okay. The first one is, ignore for 1 second this funny thing, there is IT. Okay, let's write this actually. Okay, just for 1 moment. The biggest difference is that instead of the big gamma, instead of a big matrix, I have now this small gamma. This small gamma is a number. Okay, either a constant or a function of t that might change as my iteration change. Okay, of course, there is no way in hell that this will going to be an exact computation of the ordinary least squares. In general, it's not true. There is no reason to believe that doing that n times, I'm actually going to get to the solution I would get by solving least squares with n points. Okay? There is no reason to believe that that's true, and in fact, it's not. And that's why I give myself the possibility to rename the number of iteration, which it doesn't now, can or not be one-to-one with the number of points, okay? That makes sense? So this is the main comment. And if now I want to allow myself to visit the point more than once, I have to somewhat give a symbol that says in which sense I'm, give me a rule of visiting them, okay? And that's what this is doing for us. Let me give you a few, or you give me a few possible choices. One possible choice is I say, no, I don't care. I'm just going to look at the data once, just once. I fix an order and I look at them once. I can just do IT. I can just set t equal t and then do t from 1 to n. Okay? This is the simplest case. I'm going to look at the data just once and I fix an order and I go through it. Okay? So this would be what you might want to call the one pass. But you can also consider other situations, like what? Example, you might want to just do the same thing. You look at them once, fix in an order, and then you start again. Okay? So now you have a situation where you really have to take a certain IT, and this is just a deterministic function. Okay? And this is what is called the cyclic. You cycles over the data. You put them in an order that you decide once for all, and then you cycle over them. Okay? The first case, case one.
Yeah, each point.
Mm-hmm.
And if we
So you're saying, if I do this many times, then at some point I see it as a way to invert a matrix. And if the inverting a matrix is a bad idea, why should that work? Why should this work and that one? No?
when you duplicate.
Hmm?
So
So let me wait to answer let me do this. So I want to list the different flavors of this and then comment of the interpretation of the different flavors. And then it will be, one of them will be exactly connecting to when you have many data points. And then perhaps is the better to answer the question, which is slightly complicated at this point. Okay, so remind me just in 5 minutes. So for now, let's just keep on going with this list. Let's do the flavors of this. Yes. I'm gonna want to show you different ways of viewing. In some of them the order will matter, in some of them the order will not matter. But we have to list them first. Absolutely, it's a good question. Okay, one question is, how is this related to the matrix inversion problem with more or less data? Okay, another question is, will the order matter or not? Okay, because here in some sense doesn't really matter because I'm just using the amount of data I have. Here I allow myself to choose the different order. Let's list the order in which we're going to say, and then we answer all the questions. Okay, or at least give an intuition. So first case is I look at them once, so I give it a name, whatever you want, and I go for it. Okay. Case two is I'm going to look at them more than once. I fix an order and I cycle over it. Okay. So I call the data 1 to n, and then I do 1 to n, 1 to n, 1 to n, 1 to n. Okay. In these cases, it's multiple passes. And so passes are sometimes called epochs. Okay, this is just a name people use when you look at the data, or when you do n steps and your number of points is n. What are the other two? There are at least other two possible ways of doing this, easy ones. Everything we did here is the data random, but the algorithm itself is deterministic, right? There's nothing not random in the algorithm itself. Sorry, there's nothing random in the algorithm itself. So now let's put something random, like what? time. Right, so basically what he's saying is what is called reshuffling, and he's basically saying, I'm gonna do this. I take the data set and I do like this. Then I sit there and I see it once, okay? Then when I'm done seeing it once, so I did one epoch or one pass, whatever you wanna call it, I take this and I do like this again, and I put it there and I do it again. So you reshuffle, you permute the data every time you pass over them. So this is what I call the reshuffling. Okay? Clearly here the order changes. The first case the order is given once for all, here the order changes all the time. Okay, what is the other option? Right, so you have the point sitting there and you go in and you pick a point, uniformly at random from the one you have, and then you put it back in. And then you keep on going. What is the big difference between this last case and the other ones? This is called the with or without resampling. I never remember. No, yeah, this is my problem with the with or without replacement. I get confused, my brain just collapses, but it's fine. Let's call it uniform sampling. Yeah, so on average, because you're doing uniform sampling, you're gonna see all the points roughly the same amount of time, but there might be, the first time, point twice and another point, none. Okay, so strictly speaking, when you do this, you don't do it passes over the data. It's like people like to call them sometimes effective passes or epochs. It's exactly what you just said. I'm picking point at random and I'm putting it back so I can pick it twice. And this means that if I do n steps, I'm not going to see everybody once. Okay. All right, how do we navigate this? Okay, and we're going to keep it simple, but you can start to also do some things like complicated, like for example saying, okay, on the one hand, let's compare this to the classical batch gradient. The classical batch gradient would replace this term here with a sum xi wt minus 1 minus yi square. Sorry, without the square. Okay, so this is the gradient. The batch gradient is when you wait to compute all the gradient before you actually do an output. Okay. One thing people do in practice. So I just want to discuss a bit the algorithmic solution before discussing why they're interesting. So these are potential choices you have. Of course, we didn't discuss the step size yet. One thing you might want to do is, okay, but this is a bit, okay, maybe this is too much to see all the points before I update, but maybe this is a bit extreme. I update all the time. What about something in between? Well, what is the something in between? You look at 5 points. You compute the gradients here for 5 points. And then you update, okay? And then you keep on going. You take another 5 points and you keep on going. So in some sense, you group these computations in blocks and then you update, not every time, but every time you finish looking at a group of a given size. This is what you call mini batching, and these are called mini batches, okay? What is the intuition? Why would you want to do it? We're not going to discuss much about that. The basic intuition in a sense is that this is when I put here n, this is a big average, and it's a very stable computations, whereas here I just look at one element and it may vary a lot. So maybe if I do something in the middle, I'm going to be able to have something that vary a bit less, and yet to be something quite reactive that changes up and up itself. Again, imagine that this is 10 millions, okay? You have to wait a lot before you actually see an update. Whereas if you take, say, this guy to be 100, every time you see 100 points, you go up, and until you average things a little bit. I don't know. There is a machine learning, which is basically every idea you think about, somebody tried. The typical thing that makes an idea more like successful is because at some point you can make sense of what the hell you're doing. But if you actually look well enough between 2017 and say 1962, I'm sure you find somebody who actually did that and maybe come up with the reason too. It's kind of very hard to find very new ideas. So yes, I'm pretty sure that somebody did it based on a prior though. I would say the mini batching is something that is used all the time, though. And usually one uses intermediate size mini batch, not huge. It's more perceived as a And again, these are just the story of this is again is that I'm showing you the tip of the iceberg. Okay, there are 3 gazillion tricks that are used on top of these. These are somewhat the canonical one, and it's useful for us because they point at one very basic question, which is if you want, what the hell am I doing here? The matter order. How am I using this? I'm using it just to do an optimization problem, or I can use it as a form of regularization. Okay, so these are some of the questions we want to discuss now. To discuss them, let me point out that if you look at the reason why these methods have been proposed in the literature, the reasons are very different, although related. One is that you can say, my goal is to actually minimize the expected error. So we haven't seen this symbol in a while, but remember that lying somewhere in the shadow, we have a probability, okay? And suppose for a minute that my goal is to minimize this. Let's just use let me just write this as an expectation so that I don't have to carry around the whole integral all the time, okay? And let's hallucinate a minute and just say, okay, I do have access to the distribution. Let's write down gradient descent. How will it look like? Wt equal Wt minus 1 minus gamma, and then I have the expectation, and I have to take the gradient inside because everything works fine. So I have to take x Wt minus 1 minus y, and there's going to be a 2 somewhere here. Okay? So they look pretty similar, right? The basic idea is that what I'm going to do is saying, okay, I would like to solve this, but I don't have access to this, okay, because I don't know the expectation. So what I'm going to do is I'm going to try to find what is called a stochastic gradient. What is it? It's a quantity whose expectation should be a good approximation of that, or maybe even equal to that. Any guess what can it be? This. Okay, so basically what I wrote there is essentially a situation where what I did is replacing this quantity with just xt okay? Instead of the expectation, I just take that quantity there. Okay, and the basic idea is again that here the complication is that mathematically it gets more complicated because this Wt can depend on the one before, and so here one has to take expectation with a grain of salt. He has to condition over the past, in some sense look at kind of a conditional expectation, and then you can that is the sense in which this guy is a good approximation of this. In expectation is exactly the expectation of this, the conditional expectation of this gives you exactly the gradient. Okay, so this is one potential point of view. What I wrote here is a general problem, which is what in optimization is called stochastic optimization. And the general case is when you have a function g, in our case of w, which is just an expectation random variable, let me call it z, of some function g of wz. Okay, so say I give you a function of 2 quantity, a random variable and a vector, and then I take the expectation with respect to the random variable, but I want to minimize with respect to the vector. So this is the general form of stochastic optimization or optimization of a function which is itself an expectation. This is just a special case where my g is just a loss function, and so and I'm just considering this linear parameterization. Okay, the random variable z in our case is xy. This is not important for our discussion, but it's just a pointer of the fact here we're actually sitting again on the beginning of a big topic, which is stochastic optimization, which takes that general form, where there are a lot of results about how you solve the problem, upper and lower bounds, and it's a well-known topic in optimization. Okay, I guess the idea here go back to Robinson Munro in 1950s, and it not only in learning, but in control, tracking, you name it. Okay, and this is just our small perspective on it. For what we care about, the key point is that in this perspective, the method is one way to look at the minimization of this problem. And basically the idea that you should just look at the data once. Okay? Now, if you have a lot of points, the idea is that you're actually converging to a solution of this. Okay? I guess, does it make sense? I guess now you can go back to your question, okay? And the question was basically, I guess, let's see if this is one way to say it, is, okay, I have a lot of points. Actually, I have infinite points, okay? I have to solve this. What is a good solution of this? And in which sense this converts to a solution? So which solution? Which solution among the many of that problem, okay? Is that one way to say this? What you want to? So one way to say this is basically the following. I think this might be useful for Tommy later on, so I'm going to do it. So, okay, and just do the. So let me tell you what I want to show you. I want to give you a vague intuition of the following. If you try to solve this problem, you boil down to a linear system, okay, that you will never be able to solve because the matrices depend on the distribution, but you can think about it, okay, and you can check whether it's a good solution or not. It turns out that this linear system might actually have multiple solutions, and what you care about is the minimal norm one, which is the one given by the pseudo-inverse. What does it mean? When you have something which is not invertible and you have zeros, you throw the zeros away and you invert whatever is left. Okay? You don't regularize, strictly speaking. You just remove the zeros on the diagonals. That's what this is just the spoiler of what we're going to show you. Okay? The idea is that it is possible to show that this iteration always converges to that. Okay? So step one is to show that the solution of that is simply some minimal norm solution. So I'm going to select the minimal norm solution of this problem, which is stable, so it's good. This algorithm, which is again one that I cannot solve, converges to the minimal norm solution. Okay, this gradient descent. And then the idea is that because this one is just an approximation of that, it's going to do the same. Okay, that's the basic reasoning. Doing what I just said is going to take us a while, okay? Because basically, it's not too complicated. I mean, this step of proving that this is a good approximation of that is actually pretty complicated things. You have to use a bunch of probabilistic tools. The fact that this converges to this is a standard thing about gradient descent, okay? The fact that it converges to a minimal norm solution takes a little bit of notation to do. So my proposal would be to not do it now, and I think Tom is basically going to cover this most likely when I discuss deep networks, because this is actually an interesting point connecting to that kind of problem. But does it make sense? Does it give you at least an idea of the answer? We can discuss it offline a bit. This is the basic reasoning, okay? So his concern was there is always even if you give me infinite data, at some point I have to invert a matrix, sure, but you can also state the pseudo-inverse, which is killing the zero eigenvalues, and that's fair enough, because in some sense I kill the noise, now I have infinite data. And these algorithms converge to that solution, to the pseudo-inverse solution, and the theorem is an approximation of this. So that's roughly what's going on. Okay, so the minimal norm solution, let me call this converges to minimal norm solution. So let's consider problem 0. So you say minimal norm solution of problem 0. GD, this one, converges to the minimal norm solution of 0, and 3 SGD 1 approximate GD2. Okay, so this will be the SGD version 1. Okay, so these are the 3 steps in answering questions basically, and it's a theorem. Okay, it actually requires some work. Here we don't want to go that in depth with this whole story. The first 2 facts are standard. Okay, it's linear algebra. You can prove it as an exercise. This one here is a bit more complicated. All right. So if you look in the literature of this kind of method, they appear here. And typically in this place, what you do is that you typically do one pass over the data. And the classical way to choose the step size is something like gamma n, because at this point is the same thing, is 1 over square root of n. Okay, or say gamma t is 1 over square root of n. horizon.
Just to
No, it's this. It's just this.
Oh, it's the one.
For now, it's just it because in that point of view, you take every point is an oracle providing you an information. You just take a step of the gradient. So the analysis, all the analysis that is developing this kind of stochastic approximation point of view is every point one step and that's it. When you finish the point, you finish the steps and then you don't move anymore. Okay. That's exactly what we want to discuss. Is people do this all the time? Is there somebody actually studied it? Okay, and it turns out that the answer is yes, although it's is another chapter of optimization. Any questions about this? Again, these comments here, it was mostly just to answer the question and not leave it hanging, but it's a whole discussion. Okay. So consider now a different problem, okay, which is the problem where what you do is trying to solve empirical risk minimization. So you actually try to solve 1 over n, sum I from 1 to n, yi minus w xi square, okay? Now, this is, again, a standard problem in optimization because it is not just any objective function. It's an objective function with a special form. It is a sum of functions. Okay, so it's g of w, which is itself a sum of many gi. What are the gi for us? Are just the loss at every single point. This problem appears in a lot of places. It's what you call sometimes composite optimization. Composite in a that is given by a sum of functions. The function you're looking at is a sum of functions. And the idea here is that the typical case of interest is the one where you have many elements in your sum. Okay, you happen to have a lot of elements in your sum, and you don't want a way to compute the full gradient before updating the solution. Okay, so in the first case, the point of view is you would like to compute an expectation, you cannot, you get an approximation. Here, the point of view is I just want to optimize this. Okay, and the point is that it's just a sum which is too big, so I don't want to wait. Okay, and in this case, it's very natural to actually, there's no reason why it should be a good idea to do it only once. Okay, it's true that when the data goes to infinity, you don't even care about the data going to infinity from a pure optimization point of view. All you want to know is make this iteration such that fix the number of points is going to converge to the minimizer of this. Does that make sense? In the first case, I wanted to know as the number of points goes to, the number of points and the number of iterations coincide, and I want to know as the number of points goes to infinity if I get to the true expectation. Here I'm asking a different question, which is fix the number of points, and now let the number of iterations go to infinity and check if you converge to that. That's just another question, okay? And in this case, it's very natural to look at it more than once and then allow yourself to design different way to pick. And the basic idea here is that because the data points are all similar, you might already start to exploit the data as they arrive, and you might have that a few points are very, say, representative of your whole data set, and once you take these increments, every time you get the points, you take big steps in the right direction. Okay, so that's the basic intuition for using this kind of methods. Again, you have a big data sets, and rather than waiting to average everything out, you start to pick up points. And if you have some good points that point in the right direction, you may actually take big steps in the right direction. Okay. The idea regarding the order is that in some sense, if you fix an order once and for all, if you consider now this, you have no reason to believe that. I mean, in this case, there is no natural order, right? So I the right from 1 to end an order, and why? I mean, I can pick whatever. So the idea here is that to some extent, this is the lazy version, and this is the one that says, well, I don't want to be more agnostic, okay? So I just want to allow myself to change the order because I have no reason to believe one order is better than some others. And so in a way, if you want, these 2 points of view are more natural, okay? On the other hand, you can also say, okay, but I'm going to look at the data many times, okay? So whatever order I put, at some point after a few iterations, I might just don't care with the order I choose at the beginning. And many of these questions are questions that people study these days, okay? You could stop me now and say, okay, it makes sense said. Most of the things I said are, there are papers for the last 2 years that try to make sense of this. Is this better than this? Can you quantify exactly when is a good idea to do this and that? Is it a matter of convergence when you're close to the solution, or do you imagine that the difference is at the very beginning? That, for example, these guys are going to be more aggressive at the beginning, and this one is going to be slower, but then they catch up and so on. People don't know this, okay? A lot of the theory of this has been done over the years in an asymptotic sense. So you just know whether it converges or not. And in the last few years, there has been a big push on understanding the convergence rates to at least disentangle the properties of these different kind of methods. So if you look at validation and statistical learning in the last 5 years, it's been dominated by studying different flavors and establishing convergence rates to the different objective functions, okay? So by no means this is meant to explain the magic of the different choices, because roughly we don't know. This is mostly showcasing the different flavors of the algorithm and two different perspectives which you could try to make sense of them. Okay. Any questions about this stuff? This is just a small, preview of stochastic gradient, basically. You mean at convergence or before convergence? Right. Then in some sense, suppose that you do 2, okay? Then you pick an order, and every time you get a solution, depends on what you saw before, right? And this computation is not invariant to the order in any sense. If you do if you compute the gradient, you sum all the gradients, and then you do that update, is a sum of gradients. But here, say, when you do W1 and you go to W2, you go there because you saw a certain point. If I give you another point, you get another W2. That's it. Nothing more than that. Does that make sense? Yes. No, so in this kind of algorithm, that's a good question, and the question is about the step size. And there are typically 2 regimes. One where you are really in an online scenario where the points arrive one at a time, okay? And then you want to take a step size choice that works without knowing how many points are going to arrive. And typically, in that case, you might choose something like this, okay? Or something along the line. The other scenario is the one you know how many points you're going to get, and then you can just say something based on the total number of points you're going to get. In this scenario, in this kind of composite optimization case, it's very reasonable to assume that you know how many points you get, and you can try to choose a step size based on that. In the case where when you're getting data streaming, it's much more natural to consider this other choice. And again, there is a large literature on what is the best choice. The typical game is try to make this as close as possible to a constant that is independent on the number of points and on the number of iterations. Just when you do gradient descent, if you think about it, that's what you do. You just compute a Lipschitz constant, and then you use the step size that way. In all these cases, we're doing either one or the other, but not as easy, okay? So there are a lot of studies to try to see if there are benign conditions under which you can take very aggressive step size, because this typically translates as more efficient algorithms. Okay?
So we are dealing with...
Yes, we are. And if you want, so he's asking, we are dealing with data that comes only from the same distribution. Yes, that's what this course is about. And if you want this point to one other remark I wanted to add, which is, there is yet another way to study this, where you basically assume that there is the generated distribution, you just have a sequence of W's and a sequence of X and Y, and it's fixed, you have n of them, and you view this as a way to play a game. So a player is the one that produced the data, okay, X and Y, and he can choose which one he wants, and the other player is the one that chooses the W. And then this is the gain or the cost of the game. And then the idea is that from this perspective, you get yet another way to study this when you take what is called the sequential prediction point of view, where you basically want to see, you want to try to understand the value of the game in a game theoretic sense and see what is the best way and what are the guarantees for this kind of dynamics, okay? And again, it's just a little pointer, but there is a large literature on this. And in this case, one goes in the direction, but you say, no, I take away any distribution. What you pay is that you don't really talk about, if you want to, it's a bit harder to talk about prediction in the future, okay? Because everything is just a finite horizon thing where you just play for 30 days and you want to try to play at your, okay? Yeah, that's another very good question, okay? Because here the list, if you want, what you're saying is, once you open this box, okay? Once you stay here, there's not much you can do, but once you open the box of being random, you name it, right? I did permutation, I do uniform sampling, but how about some form of importance sampling and so on and so forth, okay? And she's asking, does it make sense to go in that direction? The answer is definitely yes, and that's actually one of the things people have been doing. Again, the basic idea here is, I know that I want to approximate some gradient, okay? Either the gradient of this sum or even one of the expectation. Is there a way to choose the points here in such a way that I'm actually going better in that direction, okay? And so people try to do methods like this. The typical gist of what's going on is that you might actually have to save some of the gradient you computed before and combine them in some way. These are called aggregated stochastic methods or aggregated incremental methods. And stochastic variance reduction methods is one of the names to be used. And this has been one of the splash in the last, say, 2-3 years. Exactly, basically, try to combine, to use stochasticity at your advantage to reduce the variance of your stochastic estimates. That's a very good point. And you can keep on going. You can also try to accelerate. We mentioned acceleration briefly. You can try to accelerate and do exactly the same stuff. Yeah. Yes, and I guess with respect to the previous one, the memory, because even in this, you don't have to keep so he's asking if the advantage of this that you can throw away the data you've already seen, but even this one, you can do that, but you will still have to keep this matrix. When you go, yeah, of course. So he's asking, okay, what about if you resample? That's what I was saying. You have to keep something more, okay? The game, when you try to do a resampling, is basically to try to be able to keep something, but not the whole thing, okay? So typically the attempt is try to keep the gradients. The gradients are these guys in vectors, okay? So if you compute this whole thing, this is just this vector times a constant. And that's just one vector, okay? If you want to keep a bunch of past gradients, maybe you can try to save a bit of computation. But that's one of the challenges. Try to be able to use better probabilistic strategy without too much in memory. But there seems to be a trade-off there. But that's a very good point. Wow, good questions. Needless to say, you can kernelize everything, okay? And it's again the same story as before. And at this point, we don't do it anymore because I would just show you an induction argument when blah, 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 blah. Okay. What we want to discuss in this last 20 minutes, essentially, let's make the following observation. We basically, for now, tackled mostly the problem of, not that much how to change substantially the way we compute an estimator from a statistical point of view, but how to try to get better computations, okay? If you were to consider the kernel version of all this stuff, perhaps not completely surprisingly, the kernel matrix, the main quantity you have to deal with. So let's remember, the kernel matrix was this K, which was a matrix which was n by n, and it was given by the kernel at the training set points. Okay, so for now we're just playing with the linear stuff. If we were to consider the nonlinear case, you will have to deal with this kind of matrices. If you look at the data only, if you actually were to look at data only really once, you might be able to just look at them. So you typically have this matrix, big matrix here. And if you were able to look at it only once, you may be able to look at one row at a time. But typically, one pass is never used in practice. You only have to look at the data a few more times. And typically, you have to store the kernel matrix somewhere. Okay? So the thing is that none of the methods we've seen so far inherently is trying to reduce the size of the problem. They all try, when you go to non-parametrics, they all have to deal with this big kernel matrix. Okay? And roughly speaking, so suppose that now what you do is that you just consider the kernel ridge regression estimator. Then this is going to be an n-cube operation in time. If you consider something like GD, you might be able to reduce this to n squared t, where t is the number of iterations. If you're able to really just do one pass over the data, you can check that what you can do is to get close to almost to n squared in time. Okay, in some sense, it's like computing the gradient once. You just look at every point just once. The thing is that if you actually check the memory requirement, for all this stuff is essentially n squared. Okay? Again, I'm excluding the case where you can do just exactly one pass. Even if you just have to do a few many passes, you typically have to store the whole thing. So the thing I want to discuss very briefly is a couple of ideas of how the hell you go beyond that memory complexity. And there's no way to go around it, at least, well, it's not completely true, but the typical way to go around it is to approximate the problem. Okay? We don't try to solve, we're gonna stick to this kind of solver for now, and I'm gonna try to find ways to basically find an approximation of a problem like this that reduce the numerical complexity while hopefully keeping the essence of the method. Okay? The basic idea is gonna be, sorry, this is IJ, is gonna be either to approximate the kernel or the kernel matrix. Okay? So, the first method is what is typically related to the so-called random features. And it's actually, other than that, it's actually related to sketching, to hashing, and to ideas that are widespread in computer science and not only. The basic idea is the following. You might remember that a kernel can always be written as a feature map, okay, over some space. But in general, what is the dimension of this space? Now together we shout. Can be infinite. Do it. I mean. So now, then if it's infinite, we don't really use this. We actually go to that equation because you don't really use this, okay? It's helpful to derivation of new algorithm, blah, 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 but you don't use it. Suppose that you had this to be a finite dimensional thing. Suppose that you can actually put RP here. Then you can use it, right? It's a different story. You can really use it. And what do? Well, instead of that system over there, you introduce the matrix, okay? Phi hat, which is n by p, and assume that you can choose p smaller than n. Then if you remember, the computation you can do is phi transpose t plus lambda I to the -1 phi transpose y hat. This is the linear, that is the basic least squares, okay? If I have the choice to use both the feature map and the kernel, because the feature map is finite dimensional, I can go in that direction. What is the complexity of this? Well, the n cube becomes np square, n square become np. So if p is smaller or even much smaller than n, I have a huge gain, okay? This was if you were lucky, and the kernel you could use, the one that is sufficient for you is finite dimensional with a small dimension. What if it's not? What if you love a Gaussian kernel and you just don't have memory for that n by n matrix? This, roughly speaking, this means that, if n is the order of 50,000, maybe a bit less, 10,000, you might run this on your laptop. You can run that on your laptop, 50,000, maybe 100,000. You already need, super duper big computer. When you go to 500,000, you don't do it anymore, okay? You have to find a way to approximate things. So with the data set that are around today, this thing is dead right away. If you have 1 million points, forget it. It's not even that it doesn't work in the sense that it doesn't give you good results. It's just that you cannot run it. Clearly, if you actually have the kernel, which was finite dimension with a small dimension, then you could be just using this, okay? Well, what if you don't have it? Well, the idea is, well, can I actually try to find an approximate feature map, okay? So you basically pay the price of you saying, sorry, it's not true, I don't use the feature map of the kernel, I use another feature map, which is just approximate, okay? It's just, let me call this psi, okay? Hope it's too low. And what is psi is another thing, okay? And it's the thing that does what? It provides a good approximation, okay? We have to specify a bit what do we mean by that, why a good approximation. But the idea is that if you do have this, then you can toss the kernel. Sometimes you do the opposite of what you did when you did kernel. The kernel, you went from finite dimension to infinite dimension. Here you're saying, okay, let me go back to finite dimension because I want to use this equation rather than that. This makes sense? This is the basic idea, okay? Only the top corner there is actually nodded when I say this makes sense. So let me try again. If the kernel has a finite dimensional feature map, you can choose whichever way you want. And if the dimension is small, you can choose this. If the natural feature is infinite dimensional, you can only go that way, but you can try to find an approximate feature map, something for which you get an approximation and still go here. Let's change the name of this. Let's call it capital M. Remember that this is a choice we made. And the idea is that if m is much older than the number of points, I'm good to go. Okay, now m becomes a parameter in my hand. The idea is that the higher m, the finer is the approximation, but the more I pay computationally. Okay? You mean on the fly?
Yeah.
So what he's asking is, you mean the memory-wise or the whole thing? So, but these are kind of worst case, these are kind of a bit of a worst case. These both things are a bit worst case, okay? For example, if you really want to invert this, nothing, you have to compute the whole thing and invert it. If you're doing gradients, you don't have to compute the whole thing. So you have to do multi-matrix vector multiplication, right? So you can compute a bunch of columns at the time, and then you don't need this much memory. But then you have to swap. You have to, look at a bunch of data, compute the kernel on the fly, do a bunch of matrix vector multiplication, and keep on going. So here, everything I said, all these comments will translate on this. I'm just considering the case where I want to throw stuff in memory, pick up stuff in memory, and leave it there, okay? Just for the sake of simplicity of the discussion. You can be smarter, and you can be smarter everywhere. Doing computation on the fly. So let's assume that instead I just want to compare to the basic case where I want to pre-compute things and load it in memory and then perform computation. Then this is my way of reducing computation. How can you reduce? How can you find something that looks like this? Okay, you know already.
Variable, and there we can use a lot of approximation.
Right. So you have many ideas. One way is to just let's look. So for example, let's do an easy case. Okay. Let's do this. Okay. Let's look at this kernel. One dimension, Gaussian kernel, one dimension, no sigma, or whatever. What he's saying is, maybe one thing I could do is to just do the following: take this, view it as a function of one variable, because then I just have to shift and do a series expansion, for example, and truncate the series expansion. Sure. Why not? That's one way to go, okay? So you can just take a Taylor expansion of this and truncate it. You will get that basically you get a set of polynomials, okay? It's fine. Does it make sense?
Yeah, that's the question. It's a kernel. Can we always?
No, absolutely not. No, absolutely not. Everything we say now is for going to be specific examples. For example, if you have a Gaussian kernel like this, which is, what he's asking is, I'm using here the fact that, if I want to play this trick, I want to code this whole thing Z and just do this. And this is fine because it's a translation invariant kernel. So anytime you have a translation invariant kernel, which is any of the big classes of one we introduced, you can do that. In general, this might not be the case. So we're not going to, this idea is general, but all the examples we're going to give are specific. Okay, so the first one is going to be the Gaussian kernel, and you can go the deterministic way. I'm going to provide you the one was proposed the first time people actually somewhat and advertised this, which is the following thing. The idea is to actually write this as an expectation of something. Okay? And then to approximate the expectation as 1 over m sum I from 1 to m phi xb bi phi x prime bi, so that I can now find my feature map to be just 1 over square root of m phi x b1 phi x bm. Okay, this is the basic intuition. Let me show you how to do it. So you want to write your kernel as an expectation. Then you basically do expectation with an empirical sum. And then you view the empirical sum as a dot product of things. And you can check that this is the thing you want to take the dot product of. Okay? So this is a general way to think about it. And in fact, this is a very general thing that you can write kernels in this way. Maybe we can just do it here. Okay, this is a Gaussian. If you take the Fourier transform of a Gaussian, you get a Gaussian. Okay? So the idea is now that we're going to write the Fourier transform and then the anti-Fourier transform and see what we get. Okay? So if you do this, this is what you get. You get d omega, where omega is the frequency. Then you get e to the minus omega square. And again, there's going to be a constant here that I disregard. Then you're going to get something that is like e to the minus e omega x prime, e to the omega x. So this is the Fourier transform of the Gaussian. This is because I'm not computing the Gaussian, but I'm shifting the Gaussian. And this is because I'm doing the anti-Fourier transform. Okay? And again, Wikipedia line 45. Okay, you have this, you stare at it, and you're like, is it what I want? Well, let's check. Is an integral of something with, oh wait, it's a Gaussian distribution. So this is actually an expectation of this one variable here. And this is what? It's a function, okay? It's a bit annoying because I have the complex number, but it's a function. So if you now replace this with the sum, you're gonna have this normalizing constant that you, again, they won't matter too much. And then here you get sum I 1m e to the I omega ix e to the I omega, okay? I just replaced the integral with the sum, okay? Why not? And what are these omega I? They are numbers sampled according to a Gaussian distribution. So I have to sample vectors, in this case numbers, according to a Gaussian distribution, and that's it. Now, this is slightly annoying, okay? Look close enough, you can just check that there is a bunch of symmetry going on here because it is just a real function. And so what you can replace is this complex exponential with sine and cosine, okay? So what you can do is that you can replace and use actually as your phi I. So your phi x bi is actually going to be, instead of the e to the e omega x, actually going to be cosine of omega x plus b. Okay, so sorry, let me call this ax plus b. Where what you do is that you pick a at random and b at random. Okay, a according to a Gaussian and b according to a uniform distribution. Can be shown that if you now replace this complex exponential with this cosine, you get the same thing. So again, in this case, allow me to just go down here. You get that e to the minus x prime square up to constant is given by 2 integral 1 over 0, 1 in dB, 1 over e to the minus a square of cosine a x plus b cosine of x prime plus b. Okay? So again, 2 ideas. The first idea is I want to write a kernel as an expectation so that again I can do a Monte Carlo approximation because then I have my finite dimensional feature vector just by taking these samples. And the first example we make is the Gaussian using the Fourier transform, and then discretize the Fourier transform. And this is the basic idea. And then, just if you are a bit annoyed by the complex exponential, do an extra little calculation that shows you can get rid of them, and all you get is cosine, okay? And now, when you do this feature map, what you're doing is that you take a vector, you multiply by a number, you add the number, and then you take a cosine, and that's what you do. Because this guy is going to be a real number in the end. Okay? So there are a bunch of cancellations going on. You can just get rid of it. You basically take, you know that the imaginary part should not be there. Okay, so you work it out. It's slightly annoying, but it comes out okay. Okay, so this is one example of how to replace a kernel with the finite dimensional approximation based on the idea that the kernel is an expectation. Okay, there is another cute one that I can do in 120 seconds. So this is the case where the kernel is really infinite dimensional. Suppose that your kernel is not infinite dimensional, but it's very large. The input dimension is very large. Can I approximate the linear inner product? Okay. Well, look at this. Suppose that you take each vector, okay, and you take the following thing, where S is a variable which is a Gaussian random variable in RD, okay? So I have just my input. D is very high, and N is very high. So, you know, I can go either way, but they're both big. So I want to show you that this is true. If this is true, now what I can do, I can just sample a bunch of points and do the same thing. Let's first see that it's true. Well, if S is sampled according to a Gaussian, it means that the expectation of S as transpose is equal to the identity, just by definition. The covariance is equal to the identity. But this means that I can now massage this, just re-rotate things. And this is just equal to the expectation of X S as transpose X prime. I'm just literally just associating things differently. But this is the only thing that depends on the expectation. I put it here. So I get X yes S transpose X prime, but this is the identity. So we prove that that thing is true. Okay? It's a one-line thing I'm showing you because it's so short. Do the approximation, okay, and see what you get. You get 1 over m from 1 to m of Si x Si x prime. What am I doing? I'm doing what is called sketching. I take each vector, I hit it with a random vector, in fact with m random vectors, and obtain a new vector, okay? So this thing here, you can write it if you want as a matrix S applied to my vector. And this is my feature vector. It's going to be given up to this normalization by SIX, S1X, SMX. Okay? It's the same idea. It's just the same idea. You have a big problem where the dimension, in this case, is your linear, but the dimension is big and the number of data sets is big. You reduce the dimensionality and then you solve the reduced problem. Is it a new thing? It's the same thing. It's just the same thing. Write the kernel as an expectation and discretize the expectation, and this is the way you do it. Clearly, it's very important to take a variable here which is isotropic in the sense that the covariance is the same. Okay? This is one of the most basic ideas to solve these kind of problems. Maybe I'm just going to briefly recap and show you the other one, which is again based on simple linear algebra idea. Okay? The whole list of kernels and feature map. The game here is now to replace, you know, I show you the Gaussian kernel, I show you the linear kernel. Now the game is how general is this idea? Can you show me big classes of kernels that you can use this? Okay? All right.